sound interference. In this problem, we've got two loudspeakers being driven by the same amplifier, so that means they are in phase. When one is putting out its peak, its crest, the other one is also at a crest, so they're in phase when they start out, the two waves that are emitted from these speakers. And what we're looking for is at point P, do we get constructive or destructive interference? Or maybe something in between. So what we want to know is how many multiples of the wavelength is it from this speaker on the left to point P, and how many multiples of the wavelength is it from the speaker on the right to point P. And some of these distances are given. Let's just put them in here. Why don't I use blue for this distance? This distance from point P to this speaker was, what was it, 3.25 meters. And what should I use? How about green? From point P to the speaker was 4.5 meters. And what we are looking at now is how many multiples of the wavelength are in each one of those distances. So first of all, we need the wavelength. And we know for any wave, even sound waves, the speed of the wave is lambda f, wavelength times frequency. So that means that our wavelength is going to be v over f. And both v and f were given in this problem. Speed of sound, 344 meters per second. The frequency, 688 hertz. That's inverse seconds. And that leaves us with half a meter for our wavelength. So we want to know the distance, 4.5 meters. Is that some multiple of the wavelength? So how many multiples, how many wavelengths go into 4.5 meters? So what I'm going to do is I'm going to divide 4.5 meters by my wavelength. And that's 4.5 meters over half a meter gives me 9. So that's an integer. It goes in an even number of times. So if the wave starts out at its crest, it's going to be at its crest again at point P. Now let's take a look at the other string. Sorry, I was just doing a problem with waves on a string. Now let's look at the other distance, the 3.25 meter distance. And we want to know how many multiples of the wavelength go into 3.25 meters. And that gives us 6.5. So that's a half integer. So that means if the wave starts out at a crest, it goes through 6 complete cycles and then an extra half cycle to get to point P, which means it's going to be at a trough. So let's just, so that means that they're out of phase, is what it means, and we have destructive interference. Let me try to draw that for you. I'm going to pause the tape and try to draw that for you so you get a more visual representation. Okay, let's try this. So first let's take a look at I've sort of drawn the triangle here. We've got a speaker at this location and a speaker on the right side, and here's point P. And the speaker on the left starts out emitting a crest, and that wave, as it moves to point P, it goes through 1, I've broken them up here, 2, 3 cycles, 4 cycles, 5 cycles, 6 cycles, 7 cycles, 8 cycles, 9 complete cycles, and it's at a crest again, a peak again, just as it hits point P. That wave is at a peak. I've also drawn it here. It starts out at its crest, and it goes through 1, 2, 3, 4, all the way up to the end here, 9 complete cycles, and it ends up getting to point P at its peak. Now let's look at the speaker on the right. It also emits a wave starting at its peak, and it goes through 1, 2, 3, 4, 5, 6, and then a half of a cycle. And so when it gets to point P, it's at its trough. It's not at its crest, it's at its trough. It's at its minimum point. And if we look at it drawn this way, it starts out at its peak and goes through 1, 2, 3, 4, 5, 6 and a half cycles, and you've got a crest meeting a trough, and that gives us destructive interference.